Next presenter is James Marshall of NASA Goddard Space Flight Center. He'll be talking to us today on multiple process support in cFS, enabling safe onboard processing. James.
All right, thank you very much. I really appreciate the opportunity to get to talk to the folks here. This has been a great conference so far. It's great learning about all these new upcoming missions. And okay, so today I'm going to tell you a little bit about the work I've been doing with adding multiple process support to cFS. I work at NASA Goddard Space Flight Center with the Science Data Processing branch. Next slide, please. So don't worry, the cFS introduction is going to be very brief. I just want to point out some things that are important to the work here. Then I'll motivate the work a little and then start getting into the implementation for the multi-process support, which we then use to add some language support. Finally, we'll talk about some of the ongoing and upcoming work we have with it. Next slide, please. All right, so what is cFS? It's a flight software framework, has a bunch of reusable applications and libraries. It's been used in flight on multiple missions, and it's open source. I always like to point people to the cFS mailing list. It's a great place to start with the community. Next slide, please. But what really matters for us here right now is that it was originally targeted at embedded systems. And by that, I mean real-time operating system, typically microcontrollers without a memory management unit. So they follows a single process multi-threaded model. There's a PC Linux target that we make use of. It was originally developed for the ease and convenience of the developers so they could run cFS on their workstation. But now it's being used, it's on a few missions, it's in space. Another important feature is the services and the library functionality that cFS provides, not the user provided applications, but built into the core services. They get all bundled together when you build cFS. And finally, cFS is under active focused development. So while the APIs are mostly stable, the internals are changing. Next slide, please. All right, so let's motivate this a little bit. First goal is to increase safety by reducing fault propagation using existing operating system protections. Second goal is to support languages that provide or that are better suited to data processing applications. And to give a little more background, we're targeting something along the lines of an ARM Cortex-A type processor running Linux. We want to be able to launch our cFS application as a separate process. And that application still needs to have access to the software bus, other cFS services, and library functions. And also, we don't want to modify the core of cFS. I want to extend it because no one wants to take this flight heritage software and then apply some patch set I made to this, well-tested embedded software. Next slide, please. And I don't really need to motivate the safety argument here. I mean, folks here are working in this field. They know how important it is. But there are these new domains like small sats, CubeSats, more experimental type projects that they're running Linux. They're not using radiation hardened hardware necessarily. Sometimes they're using commodity processors, which is very good for us because it means the performance overheads I'm going to introduce later don't matter as much because they have a powerful enough processor. And these missions are also more risk tolerant, partly because they have to be due to a more restrained schedule and budget a lot of times. Next slide, please. Again, with the next slide, if you will. With the, oh, sorry, one back, please. Probably don't need to motivate the need for doing processing on board here. We've already seen a lot of great talks. I mean, Plato was talking about 24, 26 cameras and processing all that data. And as instruments get more advanced, that need's just going to grow. bandwidth is expensive and limited, and also there's opportunities to increase autonomy, which we've also seen at this talk. And we have the hardware to do this processing, and I have to give a plug to my branch's product. They make a line of SpaceCube processor cards, which are high performance and running Linux. So now we have the hardware, we want that software to take advantage. So the question becomes, what language should we support? Next slide, please. This is, back one, please. This was meant to add a little levity. Person's asking, how are you flying? And the guy's like, Python. I just typed import anti-gravity. And the joke being that every library is in Python. Next slide, please. And so because all these libraries are available, I guess, is the slides advancing for, oh, here we are, okay. Because all these libraries are available in Python, a lot of our scientific community at Goddard specifically are using Python to write code. And as a language, it's also very expressive. You can do a lot in a few lines of code. And just comparing a little bit to C, I know we all like C a lot here, but we have to admit there are a lot of pitfalls that you can run into, hopefully while you're doing your testing on the ground. And I'd like to recommend a fun book. It's Enough Rope to Shoot Yourself in the Foot. And it's all about these issues you can run into. Next slide, please. So now we're going to go on to how we implemented our multi-process support. So this was a small internal research and development project. We wanted to get an OS process to encapsulate our new cFS application. And the trade-off here is we're gaining memory isolation at the cost of performance. And this would go on to support what we needed to add the language support. It's not the only way to add language support, but it does give us those additional protections. Next slide, please. So this is a diagram that comes up all the time at Goddard on new projects. We'd like to show this nice, pretty picture and say, here's cFS and the software bus, and all your little applications are these circles, and it's a very clean and neat view. So if you go to the next slide, the OS is just seeing a pile of memory with a bunch of threads running around. Next slide. So we're adding our, I'm going to call the process application, and that's just an isolated process, isolated memory space with its own threads. Next slide. And that way, if something goes wrong there, hopefully it won't propagate to the rest of the system. Next slide, please. So here's our cFS system again. We have our core services on the left, the software bus, executive service, event service, and then our applications in the middle there. And we want our new process application to be able to interact with this. And here you have the applications. They're making function calls to the cFS core services. And to communicate with each other, they're using the software bus. Next slide, please. So accessing that software bus is one of the key parts of this. And we're taking advantage of the software bus network. So next slide, please. This is an existing application. I really have to say thanks to Chris Knight and everyone else who's worked on it. Having the software bus network application there ready to go really made this a lot easier. We're able to write a client library that acts as a node on this network, handles a handshaking, subscription requests, that sort of things. And so that's a very quick and easy way to get talking to other applications. Next slide, please. The rest of it was a little bit trickier. Next slide, please. So, next slide, please. So we have our proxy. We're going to introduce our proxy application that's going to give us access to those services. We don't actually need to go through it for all of the function calls we want to make. Some of the functions within cFS don't actually modify global data. They're side effect free. So we can call those we can package CFS as a library and call them in that instance. For the rest of them though, we need to make sure we're calling that primary CFS instance. And Proxy Application also gives us a place where we can implement other features like making sure our new application is behaving as the CFS application would, for example, when it's commanded to shut down. Next slide, please. So here we have our full process applications using our client to talk to a proxy application, which then makes function calls on its behalf. And you also see the CFS library there tied in with it. Next slide, please. If this sounds like a job for remote procedure calls, that's what we're doing. We have our process application talking to our proxy client library, which is using flat buffers to serialize the data, NNG to manage a socket interface, and then going to the proxy application, it's the same but backwards. NNG deserialized with flat buffers, gets to our proxy application, makes the function call, and then if there's a return value, it's back down that whole chain the other way. Because we're linking CFS as a library and everything was already built together in that, we have to wrap these function calls with the linker so that we can inject our own code there. We also redefine main. And then, so that proxy application, it's doing a fork exec to launch our new process. It's doing the process management. And it's also an interesting point where if you wanted to, you could, for example, implement something like triple modular redundancy at the software level for your application. You could fork it 3 times, split out the inputs, do voting on the outputs, that sort of thing. Next slide, please. All right, so on to the language support. This was another small research and development project. Because we built on the previous work, it went a lot faster, and we're able to focus on finding projects that were interested in using this integration. Next slide, please. So I wouldn't really call this a lesson learned, just more of I was naive about it. When I started this, I thought the best place to add language support would be at the socket layer. My reasoning was as long as the data passing over the socket is in the correct format, it doesn't matter what language was used to write the programs on either end. But next slide. That was kind of a dumb way to go about it, at least in this instance, because we already wrote our C libraries and every language has an interface to call into C. So we just need to write that foreign function interface. So next slide, please. It went pretty quickly. We were able to get up and running fast. We did a demo of a Python-based command line interface for CFS, which is what the picture is of here. And just for the heck of it, we decided to try out to see how well Rust would work. And using the bindgen tool that Rust provides to make that foreign function interface, was able to get a very rudimentary, very, in Rust speak, unsafe, just ugly demo, but it has a Rust program that says hello world on the CFS software bus. So that was a nice result. Next slide, please. All right, finally, I'm going to talk about some of the ongoing work. RAISER stands for Research in Artificial Intelligence for Spacecraft Resiliency. It's another project funded by our internal research and development group. And Ivana Jeezy is the principal investigator, and she's interested in using live flight telemetry to detect spacecraft anomalies. This is a research tool, so she's testing out existing AI techniques, algorithms, and also developing her own. And she was already using Python. That's what her code base was in, so it was really convenient for her that this project came along. Next slide, please. This is just a quick overview of it. On the left, you see a bunch of telemetry points. I think this was from some sounding rockets data. And you can see that this was, it was not a good flight. There was an anomaly, and you can see that there's telemetry points that hit their red limits. And on the right, you see the output from a neural net that is building associations between the telemetry points to try to predict when something's going wrong and after the fact to help get to the root cause of what happened. Next slide, please. And so we have the Razor code up and running. We're using a simulated setup with NOS3 right now. That's open source NASA product out of IVNV. It packages cFS with ground station software, physics simulator 42, and then some hardware simulators so that you can have cFS command your simulated reaction wheel and see the results in the simulator. So it's really cool to be able to get all that linked up. And you see that we have, what I'm working on here is that cFS adapter layer, pulling in data from the software bus. For now, it's just pulling data, packaging it up for Razor into a single telemetry frame, which then they can perform machine learning or whatever AI magic they're going to do, they can do it there. Next slide, please. There's a lot left to do here. Luckily, Razor's being funded, and this multi-process support will continue on under that. There's a lot of work that I'd like to do to better automate the integration. So when the Razor dev says they want this telemetry point, I need to have a better way of pulling that in. Right now, it's just a little bit too much hand coding for my liking. There's always better sandboxing we can do and explore. I am working to open source everything you've seen here, but it's a long process. And the Rust work is also going to continue on. And before questions, if you could advance the next slides, please. Next, yeah, I'd like to, well, I just threw up my name and Ivana's email addresses here in case you want to contact us and ask about this any more. Ivana's the one to talk to about the AI stuff. I also want to thank Alan Gibson, Nathan Riolo. They contributed a lot of the code. Christopher Chapman was an excellent summer intern who advanced this work. Obviously, I need to thank the Internal Research and Development program for all the funding. And thank you to the cFS developers, maintainers, and the wider community for supporting cFS and making it a viable tool for us. Thank you very much. And with that, I'm happy to take questions.
Great, excellent presentation, James. We do have a few questions in the Q&A. First question from Chris Heastand. Is any of this published? A Rust binding for CFE CFS would be fantastic.
None of it is public yet. If you're at NASA Goddard, I can point you to the repos. If you're within NASA generally, I can send you the code. I am trying to get it open sourced. I'm kind of doing it after the fact for the multi-process work and the Python support, but the Rust stuff, I'm going to try to open source it now and develop it in public. It's just a matter of doing all the paperwork, checking the boxes, getting it approved, that sort of thing.
All right, next question from Vito Fortunato. Is the cFS RAISR adapter going to become a standard app along with the cFS provision?
So right now the cFS adapter there, it's very purpose built to Razor, and I'm not sure where Razor's going to go, so it'll depend on that. Ivana is very much into open sourcing software as well, but it's still pretty early stage research project, so I don't know.
All right, and another question from Santiago Lozano. can we find more information, or where can we find more information about Razor?
Email Ivana. Yeah, she's the expert on that, and she loves to talk about her work. It's some pretty cool stuff.
All right. Just one other question. I think you answered it, though. Are there open source distributions of this work?
Soon, hopefully.
Okay.